China's Mars orbiter captures a rare glimpse of the three-eye atlas, the interstellar visitor rewriting rules. And this comes as NASA still continues to remain silent, holding back some crucial information.
China's Mars orbiter captures a rare glimpse of the three-eye atlas, the interstellar visitor rerouting rules. And this comes as NASA still continues to remain silent, holding back some crucial information. China has released new images of three-eye atlas, and these images show details that were not in NASA's last public update. China's frames show a brighter coma, a wider dust cloud, and a sharp rise in light that did not appear in NASA's earlier material. This ancient wanderer, billions of years old, passed the closest to Mars on October the 3rd, and Chinese scientists captured several incredible snapshots. These changes happened during the hours when NASA recorded nothing, which raises new questions about what was missed and why the object looked so different when China captured it. What China's new images showed, China's images revealed a transformed object. The coma that appeared in their data looked nothing like the calm and predictable body NASA had shown only hours earlier. We've got some fresh images of Three-Eye Atlas, a third ever interstellar object observed from Earth. The difference was immediate. The moment the frames were measured, the object's new shape began to stand out. The first set of images showed a surge in brightness across the entire coma. The coma, which is the cloud of gas and dust that forms around an icy core, had expanded to roughly 400,000 kilometers across. This is about 3 times the diameter of Earth and far larger than what NASA recorded before the gap. This is the first time something like that is observed, where there is a glow ahead of the object towards the sun. The edges of the cloud were sharper than expected, and the internal light readings rose inside a short window that only one nation captured. Tail direction offered the next clear change. NASA's final release showed the tail pointing away from the sun in a straight and stable line. The new frames showed a slight bend toward the sun, which means the flow of dust shifted during the blackout period. This shift can happen when fresh jets open on the surface, and the bend confirms that the object released material in a direction not seen in NASA's earlier images. From images, we also saw that this object is active, which is an indication that this object is in fact a comet. Dust distribution inside the coma also looked different. The brightness pattern suggested larger grains mixed into the cloud, which was not present in the readings NASA released before the downtime. Larger grains form when deeper layers break apart under rising heat. The layered and uneven structure in the coma supports this, since NASA's earlier data showed a thinner and smoother dust cloud. The sun is here, and the comet's here. The sun sends the solar wind to the comet. That sail goes behind the comet. Spectroscopic analysis revealed another detail. The new frames carried a stronger carbon dioxide signature than the values detected in NASA's pre-gap observations. A rise like this points to deeper ice warming and escaping into space. This kind of release can happen fast when sunlight reaches a section of the surface that was shielded before. Each of these changes appeared inside the short window that only one nation captured.
The altered coma, the bent tail, the larger dust grains, and the stronger carbon dioxide signal all belong to the part of the event that NASA never recorded. The plume of gas around it is mostly carbon dioxide, 95% by mass, based on the Webb telescope data. This is why the new images matter. They document the point when the object reacted to sunlight in a way that did not show up in Western data, and they reveal the first clear sign of rapid change in the behavior of 3 Atlas. We've got a big update, a huge update on our favorite interstellar object. It could be the biggest update in the solar system. What NASA released several images of 3 Atlas before the blackout period, and these frames showed a stable object with a thin coma, a straight tail, and no sharp rise in brightness. This comet's really cool because it does have that tail from the sun's radiation blasting it, but it also has a forward-facing tail. Nothing in those images suggested that the object was entering a more active phase. After this update, the stream of new material paused. The gap that followed is the same period China observed in full. NASA's public archive contains no raw frames from the perihelion passage. Perihelion is the point in a comet's orbit when it passes closest to the sun. Solar radiation heats the surface at this point and vaporizes ice, which makes perihelion the most active and most valuable phase for observation, and they get vaporized by sunlight before they have a chance to turn around and show up. NASA did not publish brightness curves for those hours. They did not provide new dust readings or any updated tail structure. Their next release resumed after the object had already moved away from its most active zone, which means the changes seen in the new images from China do not appear anywhere in NASA's public record. We cannot really pinpoint the nucleus size. It's partially due to the size of the object, but also is partially due to the activity. NASA described this as a routine downtime for instrument calibration, which is standard practice at astronomical facilities. The unfortunate timing was that this maintenance window coincided with perihelion, when continuous observation is most useful for understanding how an object reacts to solar heat. NASA also did not address the clear differences between their final sequence and the new images released by China. NASA showed a thin coma, but China recorded a larger and brighter one. NASA showed a straight tail, while China documented a slight bend. NASA detected a faint carbon dioxide signal, while China measured a stronger one. These differences remain open because NASA has not published matching observations from the same time period. NASA has not contested China's measurements, and they have not released alternate frames that show a similar level of activity. China recorded the hours that do not appear in NASA's sequence, and those hours contain the changes that shaped how the object looked in the new images. And we have a better idea of the orbit of this object. This might be a brand new, unknown, potentially hazardous aster. Until NASA provides data from the same window, both records will continue to show two different sides of the same event.
The missing frames also matter, because perihelion is the only point in the orbit when a comet reveals its internal structure. As sunlight reaches deeper layers, different ices vaporize at different temperatures, and each type leaves a clear chemical signal. Without continuous observations across this period, scientists lose the ability to track how the surface layers peel back and how the chemistry shifts over time. China's images captured those changes, while NASA's sequence ended before the reactions began. Another important detail is the timing of the dust release. The size and speed of ejected grains help researchers estimate how tightly the surface material is held together. This gives clues about whether the comet formed in a colder or warmer region of its original star system. China's readings documented the start of this release, giving scientists the one point in the timeline that shows how the surface responded to the rise in temperature. NASA's data, which stops before the active phase, cannot provide this baseline. How the object changed between observations. Line up both datasets chronologically and the transformation becomes clear. The comet NASA observed before perihelion and the comet China observed during perihelion are the same object at different stages of solar activity. Of the WOW signal, and 3 stellas are aligned with a probability of 0.6%. This is normal for icy bodies that travel close to the sun. The outer layers stay quiet until sunlight reaches the deeper ice. Once that ice warms, the entire surface can change within hours. NASA recorded the quiet phase. China recorded the moment the surface began to react. The first major change appears in the coma. NASA's last images showed a thin halo that faded gently at the edges. China captured a much wider halo with sharp boundaries and stronger light across the entire cloud. This expansion means that gas and dust were released from the surface during the window. NASA did not observe an interstellar visitor rewriting the rules. And this comes as NASA remains silent, still holding back crucial information. Near perihelion, heat can travel through cracks or pores in the ice and reach deeper pockets. When this happens, the ice bursts outward, carrying material that forms a brighter coma. The tail structure also changed during this period. NASA recorded a straight tail pointing cleanly away from the sun. China documented a slight bend toward the sun, which suggests that dust was pushed in a new direction. This can occur when a surface jet opens at an angle that differs from the earlier flow. Even a small jet can shift the shape of the tail because the dust is light and travels far once it leaves the surface. A very dense and massive cloud of gas and dust that is pushed away from the sun by the solar radiation. Such changes line up with activity seen in many other comets as they reach perihelion. Brightness measurements show the strongest shift. NASA detected a slow and steady rise in light. China measured a sudden increase that occurred within a short span of time. A rise like this can happen when deeper ice breaks open and releases gas in a single burst. NASA's sequence ends before this moment, which is why the sharp increase appears only in China's curve.
Deep, warm, wise African-American male voice like Morgan Freeman. Slow, soothing, powerful storytelling cadence with rich resonance and perfect dramatic pauses. This type of brightening has clear scientific examples. In our case of 3I Atlas, it looks like a fuzzy ball of light. Comet 17P Holmes brightened by a factor of 500,000 in roughly 42 hours in October 2007, when subsurface ice vaporized all at once. The change recorded in 3I Atlas is far smaller, but the pattern is familiar. Comets often show their strongest response at closest solar approach, and this response can happen quickly. Dust composition adds another layer to the change. NASA detected mostly fine particles, which come from the outermost surface. China measured larger grains mixed throughout the coma, which means deeper layers were exposed. Larger grains form when material breaks away from stronger bonds beneath the surface. Those grains do not travel far unless a fresh jet opens. Their presence confirms that heating reached a new depth during the missing hours. China's readings also improve the accuracy of the comet's trajectory, which is perfectly aligned with, and that is something that cannot be explained just by observing or imaging it. Extra measurements taken during the active phase reduced the positional uncertainty by roughly 30%. When the coma expands and jets form, small forces act on the nucleus. These forces can alter the path slightly. By capturing the moment when those forces were strongest, China added information that NASA did not have. None of these changes point to conflict between the two data sets. They describe one comet at two different moments. NASA observed the stable phase before perihelion. China observed the active phase during the closest solar pass. The differences come from the timing, and the missing hours contain the reactions that explain why the comet looked so different in each record. What this means for 3I Atlas right now. The perihelion observations show that 3I Atlas reacted more strongly to solar heating than early data suggested. Before perihelion, the comet looked calm and predictable. During perihelion, it behaved like an object under sudden stress. That short window reshaped the coma, bent the tail, and raised the brightness in ways NASA never recorded. The event turns a quiet visitor into a far more dynamic object. Only over the past decade we started finding interstellar objects. It's a new frontier. We don't know if we were visited before. The wider and brighter coma in China's images is the clearest sign of this change. A coma forms when ice turns to gas and carries dust away from the surface. In the pre-perihelion images, the cloud stayed compact and faint. During the active phase, it expanded to a scale far larger than before. That kind of growth means deeper ice layers began to vaporize. The surface did not simply warm, parts of it opened and released stored material. Changes in grain size inside the coma support this idea. NASA's data pointed to mostly fine dust. Fine grains usually come from loose material on the outer crust. China measured larger grains mixed throughout the coma. Larger grains are heavier and harder to lift. Their presence means deeper and more strongly bound material broke loose. This suggests that the nucleus has a layered structure, with old, compact ice under a softer shell. The tail shift adds another clue about the geometry of this activity.
Tails form when sunlight and the solar wind drag dust away from the sun. NASA recorded a straight tail that followed this expected line. China saw a slight bend toward the sun. In their paper is the interstellar object 3I Atlas alien technology. That bend suggests a jet on the surface pushed dust off the main stream. Even a small jet can tilt the tail if it operates long enough. The angle in the images helps point to the region where the jet formed. Brightness measurements show that this was not a slow, gentle change. NASA recorded a steady climb in light as the comet approached the sun. China measured a sharp jump within a narrow slice of time. This pattern fits a sudden venting event. A sealed pocket of ice fractures, gas rushes out, and the coma brightens quickly. After that, the brightness returns to a slower rise. NASA's sequence ended before this jump began, so the spike appears only in China's curve. The stronger carbon dioxide signal in China's spectra ties the story together. Carbon dioxide ice is more volatile than water ice at close range, but often lies deeper under the surface. When sunlight finally reaches those buried layers, the gas escapes and adds a distinct chemical trace. NASA's weaker signal implies that these layers stayed sealed during their observing window. China's stronger signal shows that the buried ices were finally exposed during the missing hours. China's updated orbit solution reveals the mechanical effect of these vents. When gas flows in one direction, it gives the nucleus a small push. This non-gravitational force can shift the path over time. 3I Atlas, it does give scientists a rare chance to study something from beyond our solar system. China's extra measurements during the active phase reduced uncertainty in the orbit. The range of possible future positions narrowed. This helps confirm that the burst did not turn 3I Atlas into a threat, while still showing that its track is not purely passive. For comet researchers, these observations are a rare chance to test models of interstellar bodies. 3I Atlas will not come back on a closed orbit. It entered from interstellar space and will leave again. Every change in brightness, tail shape, and chemistry tells something about the environment where it formed. The stronger carbon dioxide signal hints at a cold birthplace rich in volatile ices. The heavier dust suggests a long history of slow compaction inside the nucleus.
The sudden burst near perihelion shows that those layers can stay stable for millions of years and still react violently when heated. This event also highlights how much hinges on complete coverage. With only NASA's data, astronomers would see a mild and uneventful comet. With China's perihelion images added, the same object becomes a textbook case of rapid activation. That difference changes how future interstellar visitors should be scheduled for study. It shows that observatories need dense monitoring around perihelion and shorter maintenance windows when rare objects reach peak heating. Right now, 3I Atlas is moving away from the Sun and cooling. The coma will slowly shrink as gas production falls. The tail will thin and stretch into a more regular line.
Astronomers have planned follow-up observations with ground-based telescopes in both hemispheres. They want to measure how fast the coma contracts, how long any jets keep running, and whether the chemical mix returns to the pre-perihelion state. Later, all these stages will be combined into one continuous record. The calm approach seen by NASA, the sharp outburst captured by China, and the fading trail that follows will form a complete timeline. That timeline shows how an interstellar object responds to a star it did not form around. In that sense, 3I Atlas is not just a comet. It is also a sample of another system's building blocks, and the perihelion images reveal that those blocks are far more reactive than they first appeared. Why this matters? The object, if it's technological, it would maneuver some signal, or it will have some artificial lights. China's new images fill the only missing part of the entire observational record of 3I Atlas. NASA's sequence ends before the object became active. China's sequence begins during that active phase. When the images are arranged in order, the missing hours become the turning point that explains why the object looked different in each dataset. These new frames reveal changes that were not visible in any Western release. The growth of the coma, the shift in the tail, the stronger carbon dioxide signal, and the sharp rise in brightness all occurred during the period that only China observed. These features describe how the surface reacted when sunlight reached deeper layers of the comet, and they document the moment when the object moved from a quiet state to an active one. China's measurements also refined the object's trajectory. Extra data points collected during the period of strong solar heating reduced the uncertainty in its path and produced a clearer prediction of how the object will move as it exits the inner solar system. This improvement confirms that the activity recorded in the new images was real and not an error in the readings. The importance of these observations is straightforward. NASA captured the object before its response to sunlight. China captured the object during that response. Both sets describe the same comet at different moments, and the new images fill the gap that held the explanation for its change in appearance. These observations do not suggest anything beyond natural comet behavior. They show how an interstellar object reacts when sunlight reaches fresh layers of ice and dust. This behavior is valuable because interstellar comets carry chemical material from other star systems. Each measurement helps astronomers compare how different systems form and evolve. As 3I Atlas moves farther from the Sun, its surface will settle again. The brief surge in activity will remain preserved only in the frames recorded during the missing window. Those frames document the single moment when the object revealed its most active state. And that is the reason this new release is significant. It completes the record and provides the missing context for understanding how the comet behaved at the height of solar heating.